Today we will discuss about interquery parallelism in detail. So in the previous session we were discussing about the basics of I/O parallelism, and we have seen some of the mechanism used for doing partition of database or data stored in various processors or various disk that are stored in parallel. How we can do partitions on all the data by using the partitions like hash partitioning, range partitioning, and round robin partitioning, and also we have seen one virtual processor partitioning also. Now today we will discuss about interquery parallelism and some basics of intra-query parallelism. So interquery parallelism means different queries or transactions are executing in parallel with one another. So assume that we are having more processors available and we are having more number of disks available, and we need to execute more than one queries at the same time. So automatically, if you are having only one processor and one disk, we cannot do this parallelism normally. But if you are having multiple number of processors and multiple number of disks available, we can execute different queries simultaneously by utilizing the processor and disk. So it will actually increase the transaction throughput. That means it is used to scale up the transaction processing to support more number of transactions per second. So if you follow interquery parallelism, we can execute more number of transactions within a given limited time. So it is used with the applications that require more number of transactions to be executed, and interquery parallelism will be always a better choice for doing such type of applications. Now, whether a single processor version of DBMS can be used for interquery parallelism without having any more changes. So it is always possible to use a single processor version of DBMS if you are having a single processor also, and we can do this parallelism by interleaving the execution of two different queries by sharing the time and by dividing the query execution one after another by interleaving fashion. So that is also possible, but we can have more throughput if you are having different processes and different disk available in parallel. So when we use a single processor version of DBMS, we need to have the provision for concurrency control, because we are dealing with only one processor, and the same processor different number of queries will be executing, and different queries may require the same data at the same time. So we need to maintain the concurrency control. And the second thing is we need to have the provision for the recovery, because if any failure happens in between, how it can be recovered when we are having a single processor version available. Now similarly, when we use the local memories, when we use local memory of that particular processor for execution, we need to have the problem called as consistency problem, so that the data that we are accessing now must be the exact data that is present in the local cache memory as well as in the secondary disk. So all these concurrency control, recovery, and cache coherency or consistency problem must be managed when we are using the single processor version of DBMS without having much parallelism on it. So when we look into the architectures given below, we have already mentioned about shared memory architecture, shared disk architecture, and shared nothing architecture. So shared memory means we are having only one common shared memory available. If any processor wishes to get some data from the disk and need to process that, the data will be placed inside the memory, shared memory, and the processor can access that. And at the same time, if some other processor wishes to access the same data, the processor need to look into the same location, the same memory alone. If it is being utilized by some other processor, the second processor need to wait. So every time the access or the waiting or reference will be moving towards the memory that is given common to the entire processors. Now second thing is shared disk means the problem is the disk is stored separately. It is connected to the network, but every processor will be having its own local memory. So the data will be taken into its local memory and it will be processing that. In the meantime, some other processor wishes to get the same data. It may be referring to the disk, but at the same time the same data is being utilized by one processor. So the data that is residing in the disk may not be the updated one. So the data that is actually being processed by the first processor need to be updated frequently into the disk from where we are actually getting the data. So through the network, more process to be done for maintaining the updated data. In the case of shared nothing, also the same problem exists. So each processor will be having its own disk as well as its own memory, and normally these processors will process on the data that is residing at their own disk, and it will be stored into the memory, and from the memory it will be accessing that data and processing by using the processor. But if any other processor requires the same data from this particular site, the updated data must be moved towards that particular processor. So for these two, shared disk and shared nothing architecture, it is very difficult to maintain parallelism. But in the case of shared memory, the complication is actually less. But most of the time we cannot always depend on shared memory architecture due to some problems with that. So architecture, it is a very old architecture. We cannot always depend on this particular architecture. So most of the time we are focusing on shared nothing architecture, means independent processors with memory and disk that are connected in an interconnection network, and they are communicating in between for the operations or transactions or the applications that they are trying to execute. Now the shared memory, I will explain once again. Shared memory is the easiest form of parallelism. I have already mentioned that because it is even better than having a single sequential database system without having a parallel architecture. But the complicated issues are with shared disk and shared nothing architecture due to the locking, because if an item is being utilized that is to be locked, the information must be passed through the network, and logging, the system log must be maintained, the log must be communicated with other processes within the network also. Similarly, we need to have the maintenance of cache coherency. Every time the local cache memory must consist of the exact data, that is the updated data from the secondary disk database. So the cache coherency, so the system must use some better cache coherency protocol for maintaining the recent data or the updated data that must be utilized for the database operation. So shared disk and shared nothing are the difficult architecture for parallelism, but we need to have these provisions like the properties like logging, cache coherency, etc. must be maintained within the system. Now just we look into how we can maintain cache coherency within the parallel databases. So you'll see the basic cache coherency protocol that is used with shared disk architectures. So this is the shared disk architecture where each processor will be having its own local memory and they are sharing the common disk. So before reading or writing to the page, so any processor before reading or writing into the disk, the page must be locked. So if a page is being utilized by processor, that particular page must be locked for that particular processor. And the lock must be in either shared or exclusive mode. Shared means normally used for reading purpose. We are using shared lock. So if any one processor is reading a data, other processors can also read that. But if it is exclusive lock, only that particular process can access that data. Other processors cannot have the access to the exclusive locked data. Now so if it is a read, we need to have shared lock. If we are using a write operation, we need to have exclusive locking. Now on locking a page, the page must be read from the disk. So after doing that locking operation, the page can be taken into that particular process. Now after the utilization of that particular page, that means before unlocking the page must be returned to the disk. So before unlocking, the updated page must be returned back to the disk, so that we can maintain coherency, because whenever some other processor wishes to access the same data when they refer to the disk, this disk must have the final updated or recent data. Otherwise, if it is not being updated here, the data is being updated within this system, but from the disk this processor will be getting a different data, so that cannot be permitted. So we should have this cache coherency protocol to be maintained when we are using shared disk system, or even with shared nothing architecture also. So this is the basic cache coherency protocol. Similarly, we are having many cache coherency protocols available. Now the other protocols are more complex when compared to this basic protocol. When the protocols are complex, that requires only few number of database disk read as well as database writes. Now, as I have already mentioned, the cache coherency protocol for shared nothing system is also similar. Here it is that means each database page is assigned to a home processor. So this disk will be having its own page that is with the same processor. So this is the home processor. For example, this is the home processor which is having access to the database page that is located in the same machine. Now request to fetch the page or write to a disk are sent to the home processor. So every processor will be it's called as a home processor for its own local disk. So if this processor wishes to get a data from this particular disk, it will be sending a request to the home processor of that particular disk. So accordingly, we need to maintain the same cache coherency protocol here also, so that the updated data of that particular process will be given to the requested processor. So the cache coherency protocol, which can be used in the same manner for the shared disk architecture as well as the shared nothing architecture. But when we use parallel architecture, it is always better, or the best architecture is shared memory architecture, but it is very difficult to follow that architecture. It is a very old version. We are not having any enhancement on that, so we are using either shared disk or shared nothing architecture, and the most common one is the shared nothing architecture. Now we will see about intra-query parallelism. Intra-query parallelism, as the name indicates, intra-query, the same query is being parallelized, means part of the same query, one part is given to one processor or disk, and some other part of the same query is given to some other processor or disk, so that for the execution of larger queries, this intra-query parallelism is a better mechanism. So it is the execution of a single query in parallel by using multiple processors or disk. So the purpose of this intra-query parallelism is for speeding up long running queries. Long running query means it's not the length of the query. Long running means, like for example, if you want to sort some 1 lakh data from the database table. So it is not possible to complete that task within the seconds. So it requires more time. So it is a long running query. There we can split the query and given into different processes and different disk. So this is an example for intra-query parallelism. So there are two forms of intra-query parallelism. So these two are the major portions in this particular module. There are two common forms for intra-query parallelism. One is called as intra-operation parallelism and second one is inter-operation parallelism. So very important thing, intra-operation. Intra-operation means the same operation. The same operation is being parallelized. The same operation, one portion is given to one processor and some other portion is given to some other processor. These two, the same operation will be executed in parallel by distributing that task into two different or more than two number of processes or disk. That is called as intra-operation parallelism. So I'll give a quick example, like if I want to do a sort program, sorting. So portion of sorting, some if you are having some 1 lakh data to be sorted, I will give 50,000 data into one processor and 50,000 data into a second processor. So 50,000 data will be sorted here and remaining 50% data will be sorted in the second processor, so that it can reduce the total time taken for completing that sorting operation. So this forms it is better scale or form scales better with increasing parallelism, because the number of tuples processed by each operation is typically more than the number of operations in a query. So it is like the operation is a simple sort, but if you want to execute some 10 different number of queries, maybe this 10 queries will take only less time, but that single sort operation may take more time because it is dealing with more number of tuples. So when compared to execution of more than one queries, this single sort operation itself is a heavier query, so it can be divided into, so it takes more time, so it is to be distributed or divided into different number of processes. Now when we consider inter-operation parallelism, means two different operations can be given into two different processors. So we are having operation 1 and operation 2, and we are having two processes. One will be given to one processor, second will be given to the second process. So two operations can be executed in parallel. That is called as inter-operation parallelism. So the name is slightly as a slight variation. Intra-operation, the same operation being distributed among different processes or disk. Inter-operation means different operations are distributed among different processes or disk. Now we will discuss about the parallel processing of relational operations, and we will see different algorithms on the previous intra-operation and inter-operation parallelism. So when we consider various parallelism or parallel algorithms, for all the following algorithms we are following some assumptions. So for all the queries we are considering, for explaining this algorithm, we are considering only read-only queries. That means we are trying to read the contents from the database only, and we are considering only one architecture, that is shared nothing architecture, because the same architecture can be simulated in shared memory as well as shared disk architecture. So we are discussing about shared nothing architecture only. And our assumptions are, we are assuming that we are having n number of processes available starting from P0 to Pn-1. So if you take one example, like if you are having 3 processes, it will be like P0, P1 and P2, P0 to Pn-1. Similarly, we are having n number of disks available starting from D0 to Dn-1. So D0 to D2, if you are having 3 disks available. and we are considering almost we are having same number of processes and disk available in parallel. So just for explaining these algorithms, we are giving all these assumptions. Now if one processor has multiple disks, it will be considered as a single disk only. For explaining this algorithm, if assume that one processor is having more number of disks, but this is considered as only a single. So any number of disks associated with a single processor will be considered as a single disk only. So the same shared nothing that can be simulated on the other architectures like shared memory and shared disk architecture. So the same algorithm that we are using in parallel means this architecture can be implemented in the other two architecture also. But sometimes we require some optimizations when we are applying the same algorithm on the shared memory and shared disk architecture. So now we will see intra-operation parallelism. So intra-operation parallelism is the first portion of this intra-query parallelism. So intra-operation parallelism, we need to discuss about both sorting and join. So we are considering two operations. One is sorting and second one is join operation. So sorting, we can do parallel sorting in different ways. Then we can do parallel join operation in different ways. We are using different algorithms for doing this parallel sorting as well as parallel join operation. So we will see the sorting algorithms used for intra-operation parallelism. So we will be looking into different intra-operation parallelism now. Now the first algorithm. So here in this video I will just give the sorting alone. So intra-operation parallelism, we are considering the operation sorting in this particular video, and in the next video I will be discussing various algorithms used for join operation. So because join consists of more number of algorithms, join consists of around 4 algorithms for parallel joining. But sorting, we are explaining only 2 categories of sorting. So I will give the explanation on parallel sort, 2 parallel sort algorithm in this video, and join in the next video. So first sorting. So as I have mentioned, intra-operation parallelism, the same operation here we are considering is sort operation, that is divided into different processes and disk. So what are the consideration that we are doing in this particular case? So the first parallel sort algorithm is a range partitioning algorithm or range partitioning sort. So here we are choosing processes from P0 to Pm, where m is less than n minus 1 to do sorting. So it's like P0 to P0, P1, P2, 3 processes are there. Then we are having some disk also available. So now what we are doing is, so we need to have sorting on elements present in a particular database table. So assume that this is the table that is to be sorted. So every time when we are doing sorting, there will be a sorting attribute. So for example, if you want to sort a student table by using roll number, so the roll number is considered as the sorting attribute. So we need to create a range partition vector with m entries on the sorting attributes. Just like when we are studying range partitioning mechanism, we are creating some ranges. So we need to create a range partition vector with m entries. So the same pattern we are following as in the range partitioning mechanism on sorting attributes. So for example, if you are having some 1000 elements available, take some ranges like 50 50 is a very small number. I am simply taking that 50 and 100. So normally what will happen, all the values less than 50, between 50 and 100, then above 100. This is the way in which we are dividing the ranges. So what we are doing is create a range partition vector on the sorting attribute, then redistribute the relation using range partitioning. So according to these range, all the tuples that lie in the ith range are sent to processor PA. So this will send to one processor. Then this processor will be having its own disk that is stored there. The processors are given names like D0, D1 up to Dn-1. Okay. So similarly, what is to be done? The second range will move to another processor, and that is to be stored in that particular disk. Similarly, third range will move, and that is to be stored in that particular disk. So that is actually we are expecting, but the problem is this step requires more IO and communication overhead, because each range to be passed to the processor to disk, then that is to be sorted. Similarly, the second range, all the data to be moved to some other disk, and that is to be sorted separately. So this is not an easier task. So what we are doing is each processor PA sorts its partition of the relation locally. So every processor will be sorting its partition of that relation locally. So in order to reduce the communication overhead, so it will distribute the relation into different processor, and it will do the sorting locally, and the sorted results are stored within each of the processor disk. Okay, so I can give a more explanation by looking into the diagram. So let us see the diagram. So this is the example of range partitioning sort. So P0 is the processor where the entire relation is residing. The entire relation is residing into the relation that is in the processor P0, and the D0 consists of our database table, the huge table that is to be sorted, that is present in this particular processor. Now what we are doing is we are doing range partitioning, and some of the tuples will move to D1, that is present in another processor P1. Then some of the tuples will move to D2, which is part of a second processor P2. So this is P0, listen here. Now the third one, D3, it will go to D3, which is part of P3. Okay, so the procedure is very simple. A single processor with a disk that consists of our table will be doing range partitioning, and according to the range, different ranges are moving into different disks that are part of other processes P1, P2 and P3. So now with P1 we are having some tuples of the same table present. Similarly, D2 having some other portion. Similarly, D3 having some portion of the same table present. So D1, D2 and D3, these three are part of three different processes. Okay, then with P1, inside P1 it will do sorting on the portion that is received at P1. It will do a local sort. So within processor P1, the tuples received at D1 will be sorted locally. Similarly, in processor P2, the tuples received at D2 will be sorted locally. Similarly, at processor P3, the tuples received at D3 will be sorted locally. So as you know, range partition, so less than 50, 50 to 100, then above 100. So less than 50 sorted will be having some sorted order, then 50 to 100 values sorted will be in order, then above 100 the sorted values in correct order. So D1 will be having the tuples, and that is being sorted locally, and again it is being stored in the same disk. So this is actually the same disk. So D1 will be, so after doing local sort, the same disk will be having the sorted. So up to 50 the values are being sorted here. Now similarly, after sorting the set of tuples that is received at D2, after doing local sort, the same disk will be having the values 50 to 100, that is in sorted order, that is stored in the same disk. Similarly for this also, that is also stored in this particular disk. So as you know, so the first range sorted elements are present in this disk, second range sorted elements are present in this disk, and third partition that is being sorted is stored in this particular disk. So this is the portion where we are doing sorting on P1, P2 and P3, three different processes. Now one processor which initiates the transaction that consists of the table that is to be sorted will distribute the tuples into different processes and its corresponding disk, and it will do the sorting locally, and the local disk consists of the sorted elements, and finally into the, so this is actually P0 itself, into the same initial processor it will be sending the sorted data, and that is being merged here. So just pass P1 this disk data here, then pass this data, then pass this data. Here we will be getting the sorted set of table. So this is the initial table itself. So just for pictorial representation it is given in this format. So this is what is happening with the range partitioning sort. Range partitioning. So if you know range partitioning mechanism in IO parallelism, the same pattern we are following. Just by utilizing some number of processes and disk, we are doing range partitioning. According to the partition, it will distribute to different processes. It will do the sorting locally there, and the local sorted results are stored locally within the disk, and from the disk the data's sorted tuples are sent to the initial processor. There we will be getting the entire table that is being sorted format. So what we are doing here, if we utilize the same processor for doing the entire sorting, it will take more time. But now what is happening, we are distributing that into three different processes. So parallelly it will execute the same sorting on different range of values. So we are saving the time to complete the entire sorting process. So this is the algorithm called as range partitioning sorting. Now we will look into the second type of sort, that is called as parallel external sort merge. There is a slight difference. It is almost similar to the previous case. There is only a slight change. Parallel external sort merge. So previous case, initial processor, then it is distributed based on range partitioning. But here the assumption taken is the relation has already been partitioned among different disks from D0 to Dn-1. By using some of the mechanism, it is already being partitioned. So every processors are having its own data now. It is not initiated from a single processor. So every relation is having the partition data. So the data that is present in different sites, that is to be sorted, and that is to be combined together to form the final sorted result. Now what is happening is, in this particular case, each processor PA will be locally sorting that data. So the same thing we will show it in the example diagram. Now in this case we are having P1 is there, P2 is there, P3 is there, three different processes which consist of D1, D2 and D3, and these are already being partitioned. It consists of some data. By using some, maybe it may be a round robin fashion, I don't know what format it is. So okay, by using it won't be range partitioning, it will be easier, but we don't know what partitioning mechanism it is using. Either it will be hash partitioning or it will be round robin partitioning. So assume that it is round robin. So D1 will be having some tuples available, D2 some tuples, D3 some tuples. So it is already being partitioned by using some of the mechanism. Now what is happening is, with each processor, with each individual processor, it will do the local sorting on those tuples. It will do local sort on the data present in D2. Similarly, it will do local sort on the data present in D3. So we cannot simply merge these three because we don't know by using which mechanism the data is being distributed or partitioned in D1, D2 and D3. So simply merging will not be the result of the entire sorting. Sorting means the number must be ordered from smaller to the larger. So here some way it is being partitioned, some values are there, that is being sorted. Okay, similarly some data are here, that is also being sorted. Similarly some sorting is being done, but we don't know whether here the value 50 will be there, here the value 20 may be there. So we cannot simply merge these two. So we don't know in which way it is being partitioned. So after doing this local sort internally within each processor, from after this local sort, it will do the process called as range partitioning. So this will produce the sorted data on this D1 will be doing a range partitioning. So it will apply range partitioning, and some range value, first range value will go to D1, second range value will go to D2, and third range value will be going to D3. Similarly here this also will do range partitioning. First range will go to D1, second range will go to D2, and third range will go to D3. Similarly here also first range, second range and third range. So for all the processes, from all the processes, the first range will go to D1, that is into P1. From all the processes, the second range will go to D2, that is part of P2. From all the processes, the third range will go to D3, which is part of P3. Now the data in D1 will be in sorted order, in D2 will be in sorted order, D3 in sorted order in different ranges. Now it will go for merging D1, D2 and D3, and that is stored in a different processor, where we will be getting the result of the complete sorting. So this is actually called as parallel external sort merge. The difference between range partitioning sort is that in range partitioning we are distributing the relation into different processes, into different disk by using range partitioning. So initially we are doing range partitioning, then we are doing sorting, then we are doing merging. But here already it is being distributed or partitioned by using some mechanism. It is not, maybe it is not by using range partitioning. So different values will be there, the values are not within some range and all. So we are doing local sort on each of these processes. Then after that the result will be again applied to range partitioning, and according to the range the data will be. So some range partition means range partition vector will be created, and accordingly it will be sending the ranges into different disks on different processes, and these individual results will be merged into a common processor to get the final concatenated run, that is the final result of the entire sorting operation. So this is the way how we are doing parallel external sort merge. So here we have discussed about two sorting algorithm for doing parallel sort. So parallel sort is an example of intra-operation parallelism. Parallel sort can be done by using range partitioning sort, by using this mechanism. Then it can be done by using parallel external sort merge by using this mechanism. So intra-operation parallelism, give some example algorithms for doing intra-operation parallelism. So you can explain sorting algorithm or parallel sort by using these two methods. So sometimes the question may be asked like you need to explain intra-operation parallelism in detail. So sometimes you need to explain some sort algorithm, and sometimes you need to explain join. So maybe sometimes the question will be asked separately how sorting can be done by using intra-operation parallelism. Sometimes the questions will be asked like explain how join operation can be done in parallel by using intra-operation parallelism. So sorting part is over. In the next video we will discuss about different parallel join algorithms, which is also an example of intra-operation parallelism. Thank you.